So today our topics are free fall. I am not going to charge for this. ASU charges you enough. We can fall for free. And we're going to talk about solving accelerated motion problems. Hey, you got it. You get an A. Solving accelerated motion problems. I'm going to show you some tricks and tips and see how the equations that we've done, the equations that I have already introduced can be applied to discover things that seem incredibly impossible. Okay, so first, free fall. Let me ask you a question. I have an object with some mass here. Maybe I shouldn't be throwing this around. Here, who cares about this? No, maybe not. Here. I have a roll of paper towels. Does it weigh more here? Does it weigh more right here? Or does it weigh more, what does it weigh more right here? It's the same, right? Doesn't matter the position. Well, that's actually not true. If I lift this up 30,000 miles, it's far from the Earth, right? Weight does actually depend, how hard gravity pulls on stuff does actually depend on where you are. It really only depends on two things. In a while we will discuss this, not today. Gravity, the strength that gravity pulls on each kilogram of material depends on how big the Earth is, how big whatever is gravitating you is, and what shape it is, where you are, the geometry of the situation. So here on the surface of the Earth, as I will show you in a few minutes, gravity pulls with a certain strength for each kilogram of mass, and way up in outer space it pulls less hard, and in deep space it pulls basically not at all. Does the amount of stuff in this toilet paper roll, is there more matter, or are there more atoms here or here? Do the atoms change at all when I lift this up? No. Do the atoms change as I am lifting it vertically or lowering it vertically? No, horizontally. The same amount of matter is contained. As you are fond of learning in your chemistry classes, mass is conserved quantity. If I'm not breaking this in half, I don't change the amount of matter. What happens if I do break it in half? Is there more stuff when it's broken in half or when it's put together? It's exactly the same. No. The more total stuff. If I broke this in half, the total amount broken in parts is the same as if those parts are glued together, minus the glue, I suppose. Right? Okay. Last, question.
The weight doesn't change, but the gravitational pull of it changes.
The gravitational pull does change if you lift it up astronomically high. Take a scale, lift the scale, put something on a scale up, put something on a scale down. That's not going to change over the scale of your height. Go to Mount Everest. Go to the Dead Sea in Israel. Gravity does actually change measurably different. Go to the North Pole, gravity is measurably different, but it's a very small effect. Less than 1% difference, I think, if I recall correctly. The moon, the sun pole, between night and day, that's a measurable difference as well. The moon and the sun gravitate towards us as well. I'm just going to talk about the Earth, though, for today. Let's not make astronomy concerns as well. Hey, let me reflect on this. If you've got a heavy, big honking thing, and you split it into two pieces, and add up the two pieces' weight, should that be more or less than the whole thing? Yeah, same. It doesn't matter if something is broken up or put together. Okay, so last silly question here, sort of, is if I've got, a really heavy person on ice skates and my son, 9-year-old, on ice skates, and I give them an equal push, who's going to go flying and who's going to barely recoil? We're going to pretend that I have enough muscle strength to do anything at all, which is a lie. Okay. My son's going to go flying, right? Wouldn't it take a bigger push? It would take someone who actually does arm day, take a stronger push to accelerate the bigger person, to move them the same amount. As it turns out, as we're going to discuss in extensive detail next module, Earth pulls on big things more than it pulls on little things. Duh! Have a 9-year-old and a 2-year-old. My 9-year-old sits on my lap on one leg. My 2-year-old sits on the lap on the other leg. The 9-year-old is pulled harder by gravity into my leg. I lose sensation in my leg faster. But Big things also require more pull in order to move in the same way. What we're going to show later, what we're going to discuss in excruciating detail, is that the weight, weight is not the same thing as mass. Weight is not how, weight does not tell you how much of something there is, actually. Weight tells you how hard it is pulled. The weight, for now, let me say, the weight pull force. What the balls? Is this, excuse me for 1 second. Is the pen's at 58%? Huh? It's out of ink. It is. It is. It's out of ink. I didn't think that was possible, but it is. What? The tip screwed up. That makes a difference? Oh, thank you. Okay, so item one, it's sort of a no duh stuff. Every atom weighs, every atom of the same kind weighs the same. Every molecule of the same kind weighs the same. The more molecules, the more atoms, the more the Earth pulls on those, the heavier those get. And that's independent of what object that is. We're also going to discuss more later that bigger objects need bigger poles to move in the same way, pushes or pulls. Okay. Again, no duh, right? Well, hold on, I'm going somewhere with this. Motion of an object is exactly proportional. In fact, we will discover the acceleration to the pull or push on that object. If I shove my son on roller skates or ice skates or whatever twice as hard for the same distance time, he's going to pick up more speed. In fact, we'll discover twice as much speed next module. If I push twice as hard, he goes twice as fast. If I push for the same time interval. So motion is directly affected by how hard something is pushed or pulled. Let's put these three pieces of information together. Suppose I arrange to have weight force. The Earth pulls is the only significant thing acting on this object. How could I do that? I just let it go. If nothing else is touching it but the Earth's gravity, then this is going to fall, in what I call free fall. I define free fall as the only significant push or pull is gravity. The bigger this object is, the more it weighs, right? The more the Earth pulls on it, the heavier it is if it's bigger, more massive, more atoms in it, more matter. But bigger objects, bigger objects need a bigger push to accelerate in the same way. I'm going to put this mathematically. One kilogram has a weight in SI unit of 9.8, what we'll learn next chapter is newtons. 9.8 newtons is how hard the Earth pushes or pulls on it. And we'll discover there's a conversion constant. That conversion constant is the effect of the planet Earth. If you go further from the center, it becomes 4.9 or 0.1 newtons per kilogram. If you've got more stuff, it weighs more. If you go to the sun or the surface of Jupiter, that constant changes. For the sake of not writing this again, I got to say this is G. G should remind you of gravity. Please don't call this gravity, though. G is gravitational field properly. And the core of Newtonian mechanics is that acceleration of an object is how hard you push on each kilogram of its mass. Bigger things get less A. Harder pulls get more A. But that's it. This is the core equation for Newtonian mechanics. You have to push harder on a bigger mass to get the same A. You push the same amount on a bigger thing, bigger downstairs, you get smaller A. You push harder on the same thing, you accelerate more. That's sort of just everything that I said above all in one line. All right, so again, I'm going to plug in together. What if weight is the only significant push or pull? I'm going to get 9.8. I said kilograms in the first and mass in the second. I should say kilograms measure the actual amount of stuff. Kilograms times mass divided by mass. Acceleration of an object is 9.8 times mass over mass. Heavier things get pulled harder. Heavier things need a harder pull to get the same motion. As a vector, I can write down that acceleration of a freely falling object is downward. I don't know if you've ever noticed this, but Earth pulls down. Duh, right? With magnitude 9.8 meters per second squared. 9.8 newtons per kilogram. Different ways of saying this. This is called gravitational field. I think it's actually called gravitational field strength. I will always refer to it as gravitational field. And it has the same units as acceleration. G tells us how hard each kilo is pulled, but as it happens, by Newton's laws, that ends up being exactly the same thing as how hard something that is freely falling will accelerate. Please note, the direction of acceleration is downward. That does not mean gravitational field is negative. Gravitational field is a strength. Gravitational field says, how hard is each kilo pulled? If gravitational field were negative, that would say pull this way gets a motion that way. Now, if I pull something down, it doesn't go up. So gravitational field is a positive number. Acceleration is downward with magnitude equal to gravitational field. Which is going to fall faster if I drop? Well, that's a bad idea. Which is going to fall faster, a big thing or a small thing? Same. Why? The big thing has a harder pull. The big thing has more inertia. They're going to feel the same acceleration. Their motion will change in the same way. Hey, what about the up versus down thing? Moving upward, as this object rises, does Earth pull harder or weaker? No, only if you raise astronomical distance. At this height and at this height and at this height, a scale is going to say the same number. Right? You go astronomically high, you go up to satellite altitudes. Yes, you'll measure a difference. I'm not that tall. Okay, so gravity doesn't, over human distances, gravity isn't affected by motion up, motion down, position up, position down. So what does that mean? That means that as something moves up, its acceleration is the same as its acceleration downward. The acceleration of a thrown object is the same on its way up and on its way down. The time it takes to rise from now to now, that's symmetric. The first now to the second now takes the exact same amount of time as the second now to the third now. Rising and falling is a symmetric process. If I draw a graph of velocity versus time for a thrown object, velocity versus time, the slope don't change. What's the slope of velocity? Acceleration, right? Hey, real fast, while I've got it up, what does it mean that the velocity is going towards the zero? slowing down. What does it mean the velocity is positive numbers? Not slowing down. The velocity numbers are above zero. The velocity numbers are positive. What does that tell you? Moving positive direction. If we're talking about up, down, this is upward motion that's slowing down. What is upward motion that's slowing down? Right? Rising to a peak. What happens here when velocity is just about to go to the downward direction? Where is it? At the peak. Many people, say most people at first, would call this the peak. This is not peak position. It's peak velocity, not peak position. This is when the object is at peak position. Why is this at the peak position? Anytime velocity values are positive, you're moving up. This instant is when the upward motion has stopped. You've moved up as high as it's going to up. It's about to start moving in the downward direction, right? When velocity values are negative, you have downward motion. So we have reached the peak position here. Was going up, about to go down. The slope of velocity is acceleration. The fact that this is a single line tells us that the object is slowing down and speeding up an equal amount, regardless of its mass, regardless of its speed, regardless of anything. The gravitational free fall acceleration is constant and uniform. I will ask you this in like 5 different ways on the midterm, and the answer each time is going to relate to this idea. Yes, heavier things are pulled harder, but pulled harder doesn't mean moves faster. A child, and if I throw a child and a beluga whale out of the window, oh God, that's terrible. But if you did it, they both hit the ground at the same time. The beluga whale's got more inertia. The beluga whale gets a stronger pull by the earth, but those exactly balance out. Please don't test that out. Not with a child and a beluga whale. I do want to emphasize this is for free fall only, which is, again, I'm defining free fall as the only force is gravity. Is something falling when it's moving up? In English, we only say fall when things are moving down. In physics, did I say anything about the direction of motion when I said only force is gravity? No. So something which is rising, as soon as it's not touching my hand, as soon as I'm no longer giving it a push, fall, fall. It's still falling. Is it falling when it turns around at the peak? Yes. As long as it doesn't land on something and get another force, it is still freely falling. So I want you to compare the acceleration at 3 times: rising, peak, and falling. Give me a comparison. Rising acceleration, falling acceleration, turning acceleration. Which is the biggest? Which is the smallest? I'm going to call this A1, A2, and A3. Google question A. Google question A is rank these. A1 is greater than A2, is greater than A3. A1 is equal to A2, is equal to A3. A1 equals A2 is greater than A3. You tell me. I have just told you the answer. I want you to show me if you understood it here. I want you to rank with greater than, less than, or equal to signs. For a freely falling object, does something accelerate more going up, coming down, or at its peak? You would not believe how many people mess this up. I'm making a big deal about it and spending 15 minutes so far on this for a reason. If this is making perfect sense to you, if you get the connection here, then you will get like 3 or 4 questions perfectly right on the midterm. And we do not have everyone. In fact, we've got about half the class. Okay, please turn to your neighbor and argue about this for a second. Half of you got it right, half of you got it wrong. It looks like on average I've taught exactly nothing.
Not huge. Oh, so I guess I'm just talking to you. Okay, okay. I think they're only. Makes sense. Terms fall differently. I don't know if I'm right. Oh, a straight line, but essentially velocity. Oh no, velocity graph constant means it's changing at a constant rate, I guess, or the distance going at a constant rate. Accelerating. So it's accelerating at a oh, okay, okay, oh, okay, all right, thank you. It's up here, right? Okay, perfect. Correct. Yeah, yeah. You're gonna be here today or here every okay, okay, perfect, okay.
Okay, time's up. Let me make a mathematical connection and see if we can get more people correct here. I get a graph y equals mx plus b. Let's say y equals 1x plus 1. What's the slope over here? What's the slope over here? What's the slope over here? It's a straight line. What's the slope? M. What's the slope when y is negative? What's the slope when y is positive? What's the slope when y is 0? Does it change? Here's the graph of velocity versus time for a falling object. What's the acceleration here? What's the acceleration here? Same constant. What's the acceleration at the instant it turns around? The correct answer to what I was saying is Google Form B. Compare which acceleration is bigger when you're rising and slowing, when you're turning around, or when you're falling and speeding. Which has the steepest slope here? Google Form B. Let's see it. Do you catch on to what I be saying? Hey, now you're getting it. Most of you. Okay. So the correct answer is the slope of velocity versus time does not change regardless of velocity positive, negative, or 0. The acceleration is the same. That's it. The acceleration is the same. All of these are the same. Okay? All of the accelerations are the same. It does not matter when you're going up or when you're coming down. What about mass? How does mass affect acceleration? Do you think heavier things accelerate harder? Or do lighter things accelerate harder? Google question C, do heavier things accelerate harder? Or do lighter things accelerate harder? If I drop my son and my baby out the window, which accelerates harder? Wow, I'm in a dark mood today. My defense, the Aleve hasn't kicked in. I'm still depressed. Still hurts. Great, time's up. As most people just heard, mass does not affect acceleration. If it is freely falling, to the extent that I can ignore drag, two objects fall at the same rate. So if I take a piece of paper and I take my keys, oh, for God's sake, if I take a piece of paper and I take my keys, which is going to hit the ground first? They accelerate at the same rate, right? Right? Shouldn't they move at the same rate? Both of these drop from dropping, fall an equal speed. Oh, crap. Did I just break physics? No, I didn't. This is not freely falling. The force of air, the lift force of air pushing against this vertically is significant compared to its weight. The pull downward of Earth is significant compared to its weight. This is dense enough that the air, it's small area, the air can't push against this nearly as hard as its weight can. You can actually prove that. You can show that if I crumple this up, decrease the area against which the air can act. Oh, sweet Jesus. Watch, look carefully. If I reduce the effect that, for God's sake, if I reduce the effect that the air has, which fell faster? Which hit the ground first? It's exactly the same. Mass isn't any effect. Mass has no effect on how objects accelerate. Only if you have more than one force. Total force, total push or pull is what causes things to change motion. If I've got a bigger total force, then I get a bigger, or a smaller total force, then I get a smaller. But if, to the extent that only gravity acts, all things accelerate at the same rate. Question? In general, yeah, that's one of the parts. Also, air resistance is bigger for different shapes. You can have a streamlined car versus a squarish car. All other things being equal, a Ferrari is going to get better gas mileage than a Cybertruck. Yeah. All other things are not equal. There's a lot more to automotive engineering, or so I've been told. I'm not a car guy. Still. Follow-up question. Follow-up question. Google Form D, knowing what you know about acceleration, if I throw my keys up, the instant they leave my hand, they're moving upward with some speed. The instant before I catch them, they're moving downward with some speed. Which of these is faster? Google Form. Google Form D. Acceleration is symmetric. Ah, and people are clicking. It's clicking mostly. Bro. I like it. I like it, B Condes. Okay, the correct answer is this is moving upward at the same speed as this is falling downward. If you accelerate equal rates, you go equal distances, this slows down just as much as this speeds up. You lose just as much V, you gain just as much V. The speed upward and the speed downward is equal. So let me give one more question before we go to the final part of today's lecture. I'm going to throw this one down and this one up. Hmm? I threw them with roughly equal speeds, although terrible aim in both cases. I threw them with equal speeds. One goes up, one goes down. Which hit the desk harder? Google Form E, which hit harder? You know that they have equal speeds, by the way, when they reach hand height. Which of them is going faster when it hits the desk? That's the Google question. If I throw one object up, one object down, and they hit the same ground, And 90% of you clicks. I like this percentage. Okay. The correct answer is if an object thrown up returns to its original position and is going the same speed down as it was when it was going up, an object thrown up and returning to its original height, moving down in the same way as an object thrown down with the same original speed, hits the ground at the same speed. The one thrown up goes up, comes down, takes longer time, sure, because it's going a longer path, goes up and then comes down. But if it returns to its original speed downward, throw an object downward, throw an object upward with equal speed, they both hit the ground with the same speed. They both have we will discover later, they both have the same kinetic energy. That's module 3. We're not going there yet. Okay. So, a couple of facts about free fall for you here, and a couple of things to think about the nature of acceleration. I'm not going to test you on forces yet. That's next module. But I wanted to make a connection that you've all felt, real world thing that you felt. Have your kids crush your leg harder when they sit on your lap, and bigger things take a bigger push to accelerate in the same way. Those two things together, you can prove that acceleration of a big thing and a small thing is equal. Okay, anyway. Let's talk about solving problems. I have so many problems and I'm giving you a bunch of them. Let's talk about the distance that those keys fell when falling, when dropped, when thrown. Let's start with just falling. Okay. Here's a graph of velocity versus time for my keys. And then they hit the ground at this instant and suddenly accelerated very rapidly upward, which is to say they stopped moving downward all of a sudden. They sped up as they were moving downward. I'm going to tell you that the acceleration here, acceleration equals negative 9.8 meters per second. Boy, I am a really bad judge of time. I've got time, not just because of ADD, but also because of, having a stopwatch for short time things is really freaking hard. I do judge distance pretty darn well. How many meter sticks am I above ground zero here? You could fit 1 yardstick, 1 meter stick in there, right? I know the total distance covered, delta height equals about negative 1 meter. Going down by 1 meter. Let's explore what we can discover about the time and the final velocity here using nothing but the equations I already done give you. What are the only 2 equations I've taught you so far? Well, no, there's only one equation. Right? There's a definition, velocity equals change in position over change in time. That's not useful for this problem because the velocity is changing. So I can't say the total distance divided by the total time is the final velocity. That doesn't make sense. I can, however, use that the acceleration is the change in velocity divided by the change in time. What do I know? What quantities have I provided you here? I told you the acceleration, right? But I don't know final velocity and I don't know time step. What about on this side? Do I know something here? Do I know something about change in position? I have 2 equations, but both of them have 2 unknowns. I don't know V, I don't know T, I don't know V, I don't know T. Is it possible to solve when you have 2 equations and both of them have 2 unknowns, 2 equations and 2 unknowns? A system of 2 equations? Yeah, absolutely. Let's do that. There is a problem though, and that is V average and change in velocity are not the same thing. How do I get an average velocity in this case? If I say that this hits at final velocity VF, what's my average velocity? average. How do we average two numbers? Add them and divide by 2. The change is final minus initial, yeah? Right? Okay, so if I write the delta V is final minus initial, blah, 9.8. Final is what? That's the unknown. Minus initial, what's the initial when I dropped them? 0 divided by delta time. Okay. And I plug in earlier the change in position is 1 unit. How do I get the average between a final and initial if the initial is 0? I'm looking at V average now. If I start at 0 and end at some unknown, what's my average? Half of your final. 0 plus something over 2 is half of the something. So what? VF divided by 2 times delta t. I ask you algebraically to solve this for one of the variables. I'm giving you 2 equations and 2 unknowns, VF and delta t. The rest are numbers. Solve it. Ready, set, go. Solve for something, plug into the other. Ready, set, go. Google form, F. Question F is find, let's say, find delta t. Algebra those. You guys don't remember 2 equations and 2 unknowns, do you? No? Haven't you guys taken calculus? And algebra has gone out the window? Okay, here's how to solve 2 equations and 2 unknowns. Solve one of them for one variable, and then by the principle, the fundamental idea of algebra is we can replace a variable with something it's equal to. Okay, so if I've got negative 9.8 delta t is VF, I can substitute that in when I have an equation with VF in it. Okay, now I've got negative 9.8 delta t times delta t over 2 is negative 1. Can you algebra that? Can you solve for t? It's one equation and one unknown. Ready, set, go. Get a number, by the way. Also, your number should match up with what you just saw, by the way. Count for me. 1 second, 2 seconds, 3. How long does it take for this to fall? Does that take 5 seconds? Sanity check your answer. Reflect on how long that takes. I'm seeing some right answers. Algebra carefully, though. I'm seeing some wrong answers, too. Turn to your neighbor if your algebra sucks. Help each other out. This is algebra 1. You guys got this.
So instead of two, by second, fine, so I multiply by two, like multiply it here. I'll just use this, try to get rid of t, delta t by dividing it. Right, divide this. Now we're just left with negative 9.8 delta time and negative 2 delta time.
1 minute, and then I'll walk you through how to algebra.
So, yeah, oh, so you can get rid of it? Like it would cancel out or something? Yeah, so now we're just left with just this. Or delta squared. Oh. Okay, got it. We're getting on the other side. That makes sense.
Okay, 10 seconds. Give me your best shot. Fire away.
Because I'm trying to get rid of that to get on the other side.
Okay, time's up. Here's how to algebra. I have the following equation. I'm asking you to solve it. First, I have a fraction. I hate fractions. You hate fractions. We all hate fractions. How do I get rid of dividing by 2? How do I get rid of a fraction with 2 in the denominator? Multiply both sides by 2. What am I left with? How many twos do I multiply with on the left side, by the way? 1, 2 to get rid of this. Do I multiply delta t by 2 as well? No. If I have something times something and I multiply, I don't have both of them get another factor of 2. Yeah? Yeah? Okay, what happens when I have something times itself? Delta t times delta t is 2t, right? No, what's t times t? If I multiply something by itself, what's that called? Squaring. Okay, so I have negative 9.8 times delta t squared equals negative 2. Ooh, negative, negative, negative. What can I do to get rid of those negatives? Multiply by negative 1. And just get rid of them, right? Both sides are completely negative. How can I get the 9.8 away? Wait, first, what do? Do I get the square off or do I get the 9.8 off? Why do I get the 9.8 off first? The way I think of this internally is if you are evaluating this, PEMDAS says first you do squares, then you do multiplications. We're undoing PEMDAS. We're unwrapping the onion. We're unwrapping the Shrek. So we reverse the order of operations when you algebra something out. Want to get rid of that 9.8, I want to get rid of the squared. Get rid of the 9.8 first. Get rid of the multiplication before the square. Divide both sides by 9.8 and you get delta t squared equals 2 over 9.8. Oh, for God's sake, 2 over 9.8. Final question is, if I've got a square, that means divide by 2, right? No, how do I get rid of a square? Whole bunch of people forgot this step. You got t squared there, not t itself. Delta t is root 2 over 9.8. So it takes 0.45 seconds to fall a meter. Yes, no, maybe so? I multiplied both sides by -1. If I've got a negative left side and a negative right side, I can get rid of both negatives. If -5 is negative x, x has to be 5, right? That's the only value that satisfies both. You could always do the same thing to both sides, like multiply by -1, kill the negative. I want to check your, I want to check your before I wreck your intuition here. If I fall for twice the time, would I go twice the distance? Google Form G, vote for this. I am making the following proposal. If I fall for 0.9 seconds, do I fall for 2 meters? Google Form, what do you think? I will tell you in 0.45 seconds, I fall 1 meter. If I fall for 0.9 seconds, do I fall 2 meters? Google Form, what do you think? We have just discovered that we fall for roughly half a second and we go 1 meter. How far would you go if you fell for 1 second instead of half a second? Would you go 2 meters? How far would you displace if you doubled the time you fell? I'm going to show you the answer in a second. Let me ask you this, follow-up question. I'm going to help you deduce and understand a connection here. Am I falling at a constant speed or a changing speed? Changing speed. I'm accelerating. Accelerating means my v is increasing. Well, actually decreasing. My v is changing. My speed is increasing as I go down faster and faster, right? If I'm going faster, do I cover the same distance at the same time? In the first second, I'm going, on average, 4.9 meters per second. In the second second, I'm going on average, in the second of fall, actually in the second half second of fall, I would be going twice as fast. If I'm going faster, I go further. If your speed is changing, you don't cover equal distances in equal times. So here's how to calculate this. I'm going to give you some equations that just come out of solving the two that I gave you. I'm sorry, the one equation. There's only one equation in this chapter. X is V average times T, and then the definitions of what V and A mean. I'm going to give you plug in. What I would encourage you to do is practice your algebra. You're going to need to be strong in algebra. And if you write down the equations, the core equations, this one equation and the two definitions, and learn how to manipulate those, that'll help you big time in the things that are to come. But here, I'm going to give you a cheater way to do it. If I am accelerating, my displacement is vt, Wait, but if my velocity is changing, I don't just have to do V average t. I can say if I were going at the same speed, it would be VIT, initial velocity times time, but then acceleration makes me go faster and faster. As it happens, plug in the numbers. Oh, there's that factor of 2 that we got from the average part. If you add half AT squared, that affects how much further you go because of the acceleration. What happens if you don't accelerate? What's the value of A? If you're not accelerating, what's A? Okay, so if you're not accelerating, what's the equation for displacement? VIT. I mean, VI is V. If you're not accelerating, you're not changing your speed, you could just say displacement is velocity times time interval. Right? Yeah? Okay, so the second equation is somewhat magical. It's not, but it is a little algebra. If your algebra is rusty, if solving two equations and two unknowns is hard, if your algebra wants to get stronger, use the only equation plus the two definitions. Practice plugging in and solving. If it's rusty, here are additional formulas that you can use to solve for anything. For instance, here's something that I wouldn't give you on the test. James Bond drops a suitcase from a James Bond drops a suitcase from a helicopter as it's taking off, okay? That makes sense? James Bond drops a suitcase as the helicopter is taking off. What's acceleration? What would I plug in for acceleration if I want to find stuff? Negative 9.8, right? I'm going to tell you that it takes 5 whole seconds for it to hit the ground. Okay, so James Bond drops the suitcase and 5 seconds later it hits the ground. And the helicopter was moving up at 15 meters per second at the time that he dropped it. No, that doesn't work. Sorry, 5 meters per second at the time that he drops it. I'm pretty sure that is a solution. Solve for the initial height of the helicopter. If he drops it while the helicopter is rising, it doesn't instantaneously have zero velocity. Inertia carries it along with an initial upward 5 meters per second. Yeah, does that? If you're moving upward and release something, it doesn't instantaneously start moving downward. It carries up a little bit. So again, I'm telling you, it takes 5 seconds to hit the ground. Initial velocity is 5 meters per second upward. Can you solve for the displacement? Google form H. He's clinging to the skid of the helicopter, by the way, while the briefcase contains secrets that were stolen from the Russians. I don't know. It's exciting. Got to solve the problem fast because it's exciting. I'm asking for a height, an initial height. Don't tell me speed. I'm getting yeses and nos. Nuh-uh. Again, the question is, what is the initial height of the helicopter? At what point did Bond drop the suitcase from? Do you guys know who James Bond is? Yeah, right? Yeah, everyone? Yes. Just checking. Use the equations, Luke. Got a whole bunch of people not plugging into the equation that's given. Sahi, if I don't stop talking in 5 minutes and give the floor to you, start shouting at me or something. I'm I'm gonna give the ceiling and the walls to you too. Okay, here's how we do this problem. Displacement, change in height in this case. What's the initial V? What did I just tell you? How long does it take to change that V? And to hit the ground? What's the acceleration? And how long did it take to fall again? Hey, can you plug numbers into your calculator? Ready, set, go. Chop, chop. Is the answer 25? This is 25. Is the final answer 25? Did it fall up or did it fall from a height down? It fell downward, right? So displacement, should displacement be upward or downward? Displacement is downward. The initial height is the opposite of the displacement. You should get a negative. If I go from an initial height to ground, if I move negative 10 meters, my initial height is 10 meters. It's not the absolute value either. To help each other with calculators, by the way, I'm getting some wrong answers still. If you're struggling with plugging into your calculator, this is a vital core skill. You must be able to use a calculator. Question. Again, by the way, the question is, what is the initial height of the helicopter? That's not necessarily the same as the displacement. Think about that. What is initial? What is final? Okay, plugging in numbers. PEMDAS says I multiply before I add, so I could do 5 times 5. PEMDAS says that I square before I do other stuff. That's 25. 25 times negative 9.8 over 2 works out to be 147.5. At the end of the day, negative 97.5 meters. That's your displacement. Now, if I go down by 100-ish meters, if I go down 100 meters to hit the ground, what height did I start from? Right? My final height minus my initial height. My final height, I'm saying I hit the ground, is 0. Negative xi equals negative 97.5. Xi, multiply both sides by negative 1, is 97.5. Question? Which I really should say is 98 to 2 sig figs. I'm not doing sig figs in this class, though. One more question. How could I find how? Question first. 4.9 times 25 is, you are righto, righto, righto. Thank you. $123-ish, right? Right? 22? Yeah. I can multiply too. Actually, I adopted. I didn't multiply. Okay, last question. What equation could you use? What could you do to find the speed that the suitcase hits the ground with? Question I, can you give me an algebraic expression that would find the final speed after you displace this distance? Holy moly, guacamole, sana sana colita de rana. How could you find the final speed? Equation or number, whatever. Hey, looky carefully. The correct answer, by the way, is here. This is the correct answer. Don't drop these squares. I didn't say V final equals V initial plus blah, blah, blah. Look, is the triangle formula A squared plus B squared equals C squared? Does that mean A plus B equals C? No. Sum of the two legs of a triangle is not the hypotenuse. You can't just drop squares in an equation without screwing up. Not V final equals V initial plus that. If you want to solve for V final, you'd square root it. Okay, real fast, here's how I would do this problem. If I wanted to find V final, I would say the initial speed is 0. My acceleration is negative 9.8, and my displacement, is that positive or negative? Displacement. Negative, I'm going down 97.5 meters. Multiply all that together, V final equals squirt 2 times 1,000, 2,000, blah, 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 blah. Hey, what's that? Squirt 2,000? About 45. I can't mental math that. Plus or minus. When you take the square root, you don't know whether it's a plus or minus that was squared. This equation does not tell you the sign of the final velocity or the initial velocity if you're solving for that. You have to insert that by thinking about it. Which direction is the briefcase going when it hits the ground? Down, right? So the full answer, you plug this into basic physics for the velocity, you'll get it wrong, go. You have to use reasoning to think about, is it going up or down? Plug out the appropriate answer. Okay. I've given you everything. Actually, I had already given you everything with this equation and the two definitions. Hint, hint, try it this way. It's good for you. But with these additional two equations, you now really have even a straightforward plug and chug way to solve every homework problem, in addition to the ideas of graphs and free fall. I would now like to turn your attention to Mr. Sahil Gangasetti, who is a former star student from last year and who you are lucky to have as your SI. Sahil, why don't you come on up and introduce yourself? May he have a big round of applause? Oh,
Hi, thank you for the applause. My name is Sahil. I'll be your guys' SI leader this semester. You guys should have gotten an announcement from me earlier today. I don't know if you guys saw that on your Canvas. So we will be having review sessions. We'll kind of collaborate on some problems. The goal is to go over things that you guys are struggling with in the class. So I'll be kind of attending on Mondays and Wednesdays at 3 o'clock with you guys to kind of see what you guys are going over and tailor the content that we go over in the sessions towards you guys' needs. So the first session will be this Sunday at 12 p.m. It will be over Zoom. Generally, we'll have sessions every Tuesday, Thursday, and Sunday. Tuesdays and Thursdays will be 2 p.m. to 3 p.m. Those will be in person and on Zoom. The location has not yet been decided, but I will update you guys as soon as I know where that will be held. Yeah, I look forward to helping you guys out and yeah.
last year, the average grade of the people who did the SI unit was 10 points higher, one full letter grade higher than the people who did not attend the SI unit. Now, causation does not imply correlation, but causation is a leading cause of correlation. And I think you should consider very carefully, do you want to be in the group that scored on average a full letter higher? Hint, hint, hint. Okay. There was one final point I wished to make. The final point I wish to make is that I love each and every one of you. You are all awesome people. Now get out of here. See you next week. Don't forget exam coming up.